Good morning, everyone. We're going to start here in chapter 10. We'll talk more about the test. We're chatting a little bit if you had come in on it. The average probably a little lower, maybe 3 to 4% lower than midterm 3 was. But we'll talk more once we get all the scores in. Can say a little bit more about it. Our next test is, of course, the final exam, which is during finals week. We'll take it. I think it's in here. I'm not entirely sure if it's in here. But it's at a specific time where we'll all take it together. It's not in recitation. We'll do a review activity this coming Tuesday in recitation. Then we'll do a final activity on chapters 10 and 11 for reviewing those chapters. And then there'll be some, review materials that the department puts out, like practice exams for the final. I have some practice materials already posted in the daily quiz area. And we'll hopefully have a chance in class to also review topics from the earlier chapters before we come to the final exam. So as of today, we have 9 scheduled lectures left to go. I think we only need about 6 to cover the new material, and then the rest for review. So Monday for the eclipse, I was thinking, let's just cancel lecture. So I don't think anybody will complain about that. But we'll cancel lecture, so we won't have it on Zoom or make up in sort of any way. So we'll just cancel lecture Monday and office hours as well. I had already scheduled the next homework assignment to be due for Monday's lecture, so I pushed that to Wednesday. So there is not an online homework assignment due until next Wednesday. So no homework for Friday, nothing for Monday. So and so then we will talk about chapter 10. We'll probably get about 2/3 of the way through chapter 10 today and Friday. So we'll wrap up chapter 10 next Wednesday. And then, like I said, in recitation, we'll just do a review activity anyways this coming Tuesday to start to review the material from chapters 1 through 9. And so I'm probably more focusing on the earlier chapters since we just saw chapters 8 and 9 this past week. So in chapter 10, we're going to get into a unit here where we change a little bit of direction from molecular structure, molecular properties, coming from the atom to the nucleus to the bond to structure from chapter 6 through 9. We now get into a little unit on gases, liquids, and solids. So gases in chapter 10, liquids in chapter 11. We'll only briefly talk about some of the aspects in chapter 12 on solids. Chapter 12 is a real meaty chapter. It has a lot of topics in it. If you happen to have looked at it yet, we're only going to talk about a few little parts of chapter 12. So we'll spend probably half a lecture on chapter 12. And then there actually is a unit that continues into chapter 13 that you'll pick up with in 1220 if you take that class, and that's on solutions. So solutions is the first chapter of 1220, and it kind of caps off the solids, the gases, liquids, solids, and then solutions kind of unit of the book. And so, in describing gases here in chapter 10, this is something you may have seen in physics or physical science class before, just on describing sort of the relationship between the pressure of a gas, its volume, and its temperature. You might remember using the ideal gas law, PV is equal to nRT. But we'll talk about that equation. We'll describe where it comes from, how it can be derived or thought of from some relationships between those parameters. And then we'll do some problems with it and then talk about properties of gases. And then get into when they deviate from what we call ideal gas behavior. So an ideal gas is the idea that gases don't really interact with each other. And so if you think about air or any gas mixture, the particles really might bounce into each other, but they don't really react with each other. They don't stick together too often. But we will see that when gases start to approach the condensation point, as a gas begins to get to the point where it's going to form a liquid, then the molecules are going to start to stick together and experience those intermolecular forces and start to behave like what we call real gases. And then that leads into the liquid phase, and that leads into the next chapter. And so the things that probably you can get a sense of from chapter 9 that lead a particular substance to have a stronger intermolecular force is that polarity. So a molecule that has a stronger attractive force will be able to form or stay as a liquid at a longer temperature. If you think of it as a gas, if it's at a high temperature, it's going to condense at a higher temperature. If you think of a substance that has weaker forces and you have it as a gas at a high temperature and you're cooling it, you're going to have to cool it to a very, very low temperature. So if you're talking like oxygen, nitrogen, they don't liquefy until you're below 100 Kelvin. So as you're below about minus 100 degrees C, well below minus 100 degrees C, are where those gases are eventually liquefying. Okay, so some characteristics of gases is that the physical properties of gases are very similar. The real property of a gas is really how many particles of the gas are present. So gases are comprised of mainly non-metallic elements with relatively simple formulas, things like CH4, CO2, F2, Cl2. So we can characterize the formulas of the compounds of gases. They tend to have relatively low molar masses. And then unlike liquids and solids, gases will expand to fill their container. So I think we know that from elementary science. They're highly compressible, so you can have a piston and compress a gas. You can reduce its volume. And I think you probably already know that if you reduce the volume of a gas, if you decrease the volume with like a piston, then if you're imagining, a container where we're decreasing the volume of the container, that you're going to increase the pressure. So you already know that as you press on the piston, you increase the pressure. And then gases tend to have low densities compared to liquids and solids. So gases have a very low density because the particles are far away from each other, so their mass per unit volume is really low. And that's compared again to solids and liquids. And then two or more gases, when they mix, have to form what we would call a homogeneous mixture, meaning they mix randomly. So we're not going to get a heterogeneous mixture. If you have two gases that mix, you're not going to have gas A and gas B. They're going to mix perfectly together and be perfectly interdispersed. And that's because they're not interacting particles. So there's no interaction between the particles, so there's nothing that's going to keep A together at the bottom of a container and B on top of it. So gases will interdisperse in a container. And so then the properties that define a gas sample would be its temperature, its pressure, and its volume, and then also how much of the gas there is. We usually express how many moles of the gas that there are with the symbol N. So we have the relationship. You may have seen this equation before. I like to lead with it because if you've seen it before, then you can think of this equation. This is the ideal gas law equation. So it's the ideal gas law equation, and it works for ideal gases. It works for non-interacting gas particles. So the ideal gas law only breaks down when the gas particles start to experience that intermolecular force with each other. There's also a slight bit of an issue on what volume we should use here, whether we should use the container volume that the gas is occupying inside of, or the free space volume, how much space is left over once you consider how much space is occupied by the particles. So we also have a little bit of an issue of that the gases should occupy a very small portion of the container. So once the gas particles start to occupy a large portion of the container, we'll see a breakdown in the ideal gas law. We'll talk about that issue at the very end of the chapter. But I just want to mention that the ideal gas law also has a little bit of an issue that the gas particles are sort of very small compared to the container that they're occupying. And so let's think a little bit about pressure. We're going to do a quick little demo here. Let me get this hot plate warming up here. So pressure is can be defined from physics as the force that's applied to a square area. And so if you think of like atmospheric pressure, you can think about how you have the force of the atmosphere. So the force is a mass times an acceleration. So you can think for like atmospheric pressure on the surface of Earth, we have the weight of the atmosphere above us that's being accelerated to the surface of Earth with gravity. So you can think how you have atmospheric pressure is due to however much mass there is above us that's being exerted onto the surface area of the Earth. And if you were to do, I used to do this calculation, it's very kind of laborious in terms of conversion factors, but you can kind of look up the atmospheric mass of Earth. You can look up the surface area of Earth, and then you can look up gravity, and you can kind of do a conversion and see that for every square meter, there's about 10,000 kilograms sitting on top of every square meter of Earth. And you have about 10,000 square meters being accelerated towards the surface of Earth at a ratio of about 9.8 meters per second squared by gravity, which gives a surface pressure of about 100,000 of those units, kilograms, meter to the -1, second to the -2. I wouldn't worry so much about these fundamental SI units, but they define the SI unit of pressure, the Pascal. Now, we talked about like the SI unit of the joule. If you remember, 1 joule was 1 kilogram meter squared per second squared. So SI units often are derived off the fundamental or base SI units. And so we see here that the SI unit of pressure, about 100,000 Pascal, is the atmospheric pressure of Earth, where every 1 Pascal is a kilogram meter to the -1, second to the -2. And so on one hand, you just have a conversion factor for Pascal to its fundamental units, and then you have that the actual surface pressure on Earth is really high with this particular unit. Now, of all the units that are SI units, this is the one that we probably use the least frequently. Pascal is really not used that commonly for gas pressure, so we'll talk in either the next slide or the slide after about a couple of conversion factors to other more common units that we use. One of them is that we tend to say that standard atmospheric pressure is just 1 ATM. So you might know that 1 ATM is kind of what we call the standard atmospheric pressure, and that ends up being equal to exactly 101,325 Pascal. So you can see that standard atmospheric pressure is about 100,000 Pascal. Okay, so another thing that I wanted us to think about is how if you think of a vacuum, if you create a vacuum and remove as much air as you can, it's impossible to create a perfect vacuum. But if you have a container where you remove all or as much air as you can remove, that you create a sort of environment where the environment could shrink if there's not enough force to hold that container together. And so what I thought we would do is take one of these pop cans that has a little bit of water inside of it, and we're just going to get this heating up where we just want the water to start boiling, and we want to have the inside of the gas in the container to be kind of at the boiling point of water. So it might take a couple of minutes for that to start kind of boiling. But once this gets sort of hot enough, the inside of the can will be sort of at the boiling point of water, and then I'm going to invert the can into a water bath, which is going to quickly cool the inside of the can. And so then we have the air that's really hot, we cool it really quick. We're going to decrease the pressure inside the can, kind of create instantaneously a vacuum, and we're going to see that the can probably can't hold up to that pressure, or the loss of pressure that we create, that vacuum we create within the can. So once that gets going, hopefully we'll be able to show what it looks like to kind of like almost crush a can just using atmospheric pressure, but by trying to create a vacuum inside the can. Well, that's up. Let's talk about a couple of pressure conversions. So 1 atmosphere, we mentioned that the ATM is probably one of the more commonly used pressure units in our class. It's equal to a unit sometimes we call either torr or millimeters of mercury, where these two units are synonymous with each other or equal to each other. But 1 ATM is equal to 760 torr or 760 millimeters of mercury. And then the way you can measure atmospheric pressure could be using something like a mercury barometer. Or mercury barometer, you would take a tube that's been evacuated with air, and then you would dunk that tube into the dish of mercury, and then the mercury will flow up into the tube until the height of mercury is counterbalancing the mass of the atmosphere that's pressing downward onto the dish of mercury. And so the height here just becomes equal to atmospheric pressure in the units of millimeters of mercury. And so here you're just literally taking the mass of mercury to counterbalance that 10,000 kilograms per square meter that's sitting above that dish. And so you can take the height of the column. If atmospheric pressure is higher, the height goes up. Atmospheric pressure drops, it goes down. I don't think, other than if you guys happen to do a lab on this and read a barometer pressure in the lab, that's probably the only time you'll ever have to encounter a barometer is in the lab. I don't think we tend to ask too many questions on making a barometer reading, but it's just a way to measure atmospheric pressure. And so then it also then kind of tells you why one of the units has a unit of millimeters of mercury, because the mercury is the sort of, its density being really high allows the column to be relatively small. And so the height of a mercury barometer has to be about almost 2 meters in length to be able to measure out to 760 millimeters. And so the mercury column will be pretty big, so you can measure the actual height relative to the base of the dish. If you imagine we used water instead of mercury, if we tried to make this out of water, well, that would probably be a bad choice because the water would evaporate. But water is also a bad choice because water's density is 13.5 times less than that of mercury. So this would have to be 13.5 times taller if we wanted to make a barometer out of water. So we choose a material that has a density. The density of mercury is about 13.5 grams per milliliter. The density of water is about 1 gram per milliliter. I can hear the water boiling over there, so I think that's ready to go. And so it would just take a lot more water to create a column. So we'd have to have a column that's like 13.5 meters high if we wanted to use water. Okay, so hopefully this works. I can see steam coming out of the can. It just means that the can's hot. So I just want to take this and work. Let me try it one more time. That's why they give me 2 cans. So it's supposed to crush the can. Maybe I didn't let it sit long enough. Let me let it sit another couple minutes, and hopefully we'll see that invert. Okay, so if we wanted to make the barometer out of water, it would just be a lot taller, and then there's not many materials that have a greater density that are liquids other than mercury to make a barometer out of. Okay, and so some other units here, we see the Pascal conversion. The unit of bar, sometimes used in meteorology, is related to the Pascal. You can see that it's the same number. It's just basically the Pascal conversion divided by 10 to the 5. And so it's 1.01325 bars, 1 ATM. And then this unit here is used in like gas cylinders. It's also used to fill our car tires. So that's 14.696 pounds per square inch. And so a PSI is a pound of force that's exerted per square inch. And so if you think of force exerted per area, this is kind of where the pounds per square inch comes from. And so when I think of a vacuum, like if I used to work on this vacuum system where we had a wall for a vacuum chamber that was probably about 2 meters by about 1.5 meters, and it was pretty deep in terms of the vacuum chamber. And so then if you think about trying to remove that door, it's like that door, when you have a vacuum created inside of there, is being held into place by 15 pounds per square inch. So if you think of how many square inches there are, let's say there's probably well more than 1,000 square inches in that sort of door. To be able to pull the door off, I'd have to exert about 1,000 times 15 pounds of force to be able to remove that door. So in other words, I'm not pulling that door off without releasing the pressure. And so you can see that by creating a vacuum, you could create a lot of force that you have to be able to hold in. So our vacuum chamber was made with like 3-inch thick steel so that it wouldn't cave in. Hopefully we can get the can to cave in because it's kind of a cool demo. If I can't get this to work, I'll just post the video of it to the video site. But anyway, so we can measure atmospheric pressure using a barometer. We can convert to different units, such as from ATM to millimeters of mercury. That's probably the most common conversion we'll use in this class. We'll give you conversion factors for these on the exams, so you don't have to have these memorized. And then you could also convert to Pascal or bar or pounds per square inch, but those aren't as common of conversions. So the most common conversions are the ones on the first line here that we'll be making. And so we can convert just to make sure that we go through a couple different conversions. So if we have a pressure of 745.0 torr, well, the first thing we might do is just recognize that that would be exactly 745.0 millimeters of mercury. And so the millimeters of mercury to torr, it's the exact same number. So they have the same relationship to 1 ATM. So 760 torr is 1 ATM, 760 millimeters mercury is 1 ATM. So they're the same number as each other. If we want to calculate the number of ATM, then we just take the 745.0 either torr or millimeter mercury value, and then just 760 torr per 1 ATM. And that's an exact conversion, so there's exactly 760. So anytime you see a conversion factor, it's either exact or we'd want to look up and see if it was rounded. This isn't rounded, this is an exact conversion. So I'm going to keep 4 sig figs. So I get 0.9803. So this is almost an atmosphere. So this is going to be a big number of Pascal, right? Because the Pascal, 1 atmosphere in Pascal is over 100,000. So the number of Pascal. I'll go back to the 745.0. We could have started with the ATM value as well. But I might do the conversion this way here. 760 torr is equal to 1 atm, and then 1 atm is 101.325 Pascal. So I can make this conversion right here like this. I could write it in 2 steps if I need to. So I could have written this in 2 steps by writing that 760 is an atm, and then 1 atm is 101.325 Pascal. Almost ready to go. I want to make sure it works. So 745 divided by 760 times 101.325 is 99325. And so we'd write that 9.933 times 10 to the 1, 2, 3, 4 Pascal. But you really have to do this quick. Maybe that's what. There it went. So again, what we were trying to do is we were trying to heat up a gas so that we were at a hot temperature inside the can, and we were trying to quickly get that into a cold water bath, where the cold water bath is going to quickly cool the gas, and then when the gas cools, we reduce the pressure inside the container, or the container tries to reduce its pressure, but it just can't hold on to that low pressure and caves in. And so that's why, for example, our vacuum chamber we would make with really thick steel so that it wouldn't just cave in when we try to create that vacuum. That's how you can crush a can just with atmospheric pressure. Okay, one last conversion is over to PSI. Now the PSI unit is, like I mentioned, most commonly used to fill like your car tires. Something interesting, whenever you fill like your car tires to say 35 PSI, you're filling them to 35 PSI above atmospheric pressure. So whatever the atmospheric pressure is that day, your car tire has that pounds per square inch above atmospheric pressure. So it's kind of like a gauge reading. And so you're actually filling your car tire with an atmosphere plus that pressure. So like if you think of filling your car tire, for example, to 35 PSI, this is completely irrelevant for probably any like type of exam question. But if this is your tire pressure, then the actual pressure would be equal to 35 PSI plus atmospheric pressure. So that's just the pressure in your tire above atmospheric pressure. And so like when you use a tire gauge, same thing. It's reading the pressure. That's why if you've ever used a tire gauge on your car tire that's empty, if you ever put it on, it hasn't moved at all. You have a flat tire. And it doesn't move at all because it's at 0 relative to atmospheric pressure. So it's at a pressure of 0 plus atmospheric pressure. An empty tire is just at atmospheric pressure. And so atmospheric pressure is about 14.7 PSI. So your tire has about 50 PSI in it total when it has a gauge reading of 35 PSI. There's only one time in my life where this was really an interesting thing to know. This is so long ago. How many of you guys ever heard of the Deflategate scandal with Tom Brady about 10, 15 years ago? And whenever people were doing the calculations to see when you go from one temperature that's hot to a temperature that's cold, how much would the pressure drop in the football, they were all just using the actual PSI reading. A football's filled to only maybe like 6 or 8 PSI, but above atmospheric pressure. If it were only 6 to 8 PSI, it would be well below. It would be a very flat football if that were the case. But if you actually included the correction of adding atmospheric pressure, then the footballs were clearly just deflated by air and not really by some scandal. So it seemed like just like the actual application of what a PSI would have been really helpful for people to know back then. So I don't know if this will ever be helpful for anybody, but I just like talking about that. So, but to convert to PSI total, the pounds per square inch for 745 torr, this would just be 1 torr, or excuse me, 760 torr is 1 atm. and then 1 atm is 14.696 psi. And we could have done that in one step probably too, but just showing it out in 2 steps. So that's 14.4 psi. And if you're for some reason trying to measure a tire pressure at that pressure with a gauge, then you're going to probably pick it up to be very close to 0, because if the atmospheric pressure is about that same pressure of 745 torr, then when you go to measure the pressure, it's going to appear to be 0 on your gauge reading. So just know, if you're filling your car tires, you're probably picking up a gauge reading the pressure above atmospheric pressure. But again, those are just a couple conversions from different units, and probably these ones here you'll see are the ones that we use more commonly in this class. Okay, now how do we measure the pressure of a gas? I kind of just show this briefly here because this is classically how you would measure the pressure of a gas, is kind of using something called a manometer. But the way you really measure a pressure of a gas these days is with a digital pressure gauge. I mean, do you guys ever use mercury? Like, what were the McLeod gauge? Do you guys still, do you even know what that is? Okay. Yeah. Some labs still have, like, I would measure pressure in a vacuum with something called a McLeod gauge. It's something where you like flip it back and measure the height difference. But much easier if you have a digital pressure gauge. But so you can use something called a manometer to measure the pressure of a gas. Again, probably not something you'll see other than just maybe picking up the example here that if you imagine having a gas inside of a container, imagine this valve is closed. Imagine we haven't opened up the valve to our manometer. You'd want to start with the mercury equal in your manometer before you open up the valve to the gas that contains your gas you want to measure the pressure of. And then you open up the valve that has some sort of pressurized gas, and a pressurized gas will press the mercury downward in the side connected to the gas. And then you can measure the height difference. And so if you're using mercury, that height difference becomes the differential compared to atmospheric pressure. And so if your gas has a pressure above atmospheric pressure, then you take the pressure of the gas to be atmospheric pressure plus the pressure from that height difference. And so think of this as just being the millimeters of mercury, and think of this usually being in a unit of millimeter of mercury. So you measure the height difference in millimeters, you measure the atmospheric pressure in the same unit of millimeters of mercury, and then you just add the two up, you get your higher pressure. And then if the gas happened to have a pressure below atmospheric pressure, so what if the gas was less than atmospheric pressure? Well, when we open up our valve, the mercury in the side connected, so we'd start again with the mercury equal in height, but the side connected to the gas sample will go higher because the vacuum will pull that mercury side upward, and then you'll have a gas sample manometer that looks like this. And so then the pressure of your gas would just be equal to atmospheric pressure, and then subtract the height difference. So then you subtract the millimeters of mercury that you have in difference between the two heights. Again, not a big detail. I don't think you'll really see, you might see maybe a homework question on this. I doubt you'll see anything like this on the test. We'll look at a review problem on this once we get to the end of chapter 10 and kind of get through this. But it's really just a simple task of calculating that height difference. Think of it in millimeters, think of it in millimeters of mercury, and then just relate that to the pressure of atmospheric pressure in millimeters of mercury in that same unit. So the key would be, when you're doing this difference here, have them be in the same unit of each other, such as millimeters of mercury, since you're usually making a mercury manometer. So the material in the manometer is mercury, so that's why you're comparing the atmospheric pressure in millimeters of mercury to the height difference using that mercury material. But probably the key, like usually any time this has ever been asked, it's always like, here's a manometer, here's a picture of a manometer. Like for the gas sample, if the side's higher, the mercury's higher on the gas sample side, its pressure's below atmospheric pressure. And if it's the opposite, if it looks like this, then your gas sample has a higher pressure than atmospheric pressure. So the only way that we've tended to ever ask this historically is just to really kind of show you a couple different manometer pictures and ask you which one would correspond to a gas either above or below atmospheric pressure, as opposed to actually physically calculating the pressure. Okay, but I just wanted to have a little slide on classically how gas pressures have been measured sort of historically. So Historically, they've been measured using a mercury manometer. Okay, now let's get into the sort of behavior, the relationship between the pressure, temperature, volume, and amount of gas. And so Boyle's law, probably not a name you need to memorize, but Boyle studied the relationship of pressure and volume and found that there's an inverse relationship. And this is the same relationship that we were talking about earlier, that if you imagine taking the volume and decreasing the volume of a gas with a piston, you increase its pressure. So if you decrease the volume and you increase the pressure, then that's an inverse relationship. And so as we imagine lowering the volume of a sample, notice that you're increasing the pressure of the sample. So maybe at 1 liter, we're at 1 atmosphere, but if we reduce the volume to half a liter, then we're at 2 atmospheres. So we're increasing the pressure as we decrease the volume. So as the volume decreases, our pressure is increasing. And so that's just what, so like a downward curve is what the inverse relationship looks like. Charles' law studied the relationship of volume and temperature. It's kind of what we were looking at here with our little demo that we were doing, where we had a hot gas and we were cooling the gas. And so when we change the temperature of a gas, we can change the volume of a gas. So what we were doing is actually changing the volume of the container. So the tin foil changed the volume. The volume of our gas was dropping as the temperature dropped as we put that can into the ice bath. And so if you imagine the opposite, if you imagine increasing the temperature, say, of a balloon, then you would imagine the balloon would expand as a result. So we get a direct relationship between volume and temperature. So if you increase the temperature of a gas, you increase its volume. And one of the keys here is that this is assuming that the amount of gas and the pressure are constant. So this is assuming that the moles of gas inside the balloon are constant, not changing, and that the pressure isn't changing. So the pressure is the same. That allows the volume of the balloon to expand if we change its temperature. And the same thing here, that if we take the volume over, as it relates to an inverse relationship to 1 over pressure, that the quantity of gas and the temperature are constant. So something that we can actually write for Boyle's law is that we can write that the sort of volume times the pressure is equal to a constant. And then we could write for Charles' law that the volume divided by the temperature is equal to a constant. And then what this means is that if you imagine changing some initial volume and some initial temperature, and then you don't allow N or P to change for Charles' law, that you can then say, well, if we had V over 2, or V2 over T2, if we change the volume, we accordingly change the temperature, that those are equal to the same constant. So these are equal to each other. The two constants for V1 over T1 is equal to a constant, V2 over T2 is equal to the same constant, so therefore V1 over T1 is equal to T2 over T2. So if they're equal to the same constant, they're equal to each other. And if that doesn't make total sense, once we come back to the ideal gas law in a couple of slides, hopefully we can look at the ideal gas law and see that this relationship would be true, that if you take the initial volume, initial temperature of a gas sample, and you change the volume, the temperature will change accordingly to this equation, because V1 over T1 is equal to a constant that's the same constant for V2 over T2. And the same thing, if you change the pressure and the volume, if you have some initial pressure, initial volume, that's equal to a constant, and then that same constant would be equal to P2 over V2. If we change the pressure, we have to change the volume accordingly. Hence, P1, V1 is equal to P2 times V2. So these two would be equal to each other. So P1, V1 equal to P2, V2. And again, we'll be able to pick those relationships up from the ideal gas law once we come back to that in a couple moments. And so a couple problems we could solve would be that if we knew the volume of a gas was 2 liters and the pressure of the gas sample was 2.0 atm, we could try to calculate the pressure the gas would have if the volume was reduced to 1 liter. So if we change the volume, what's the pressure of the gas? Well, if you notice, we have a P1, V1. So our P1 is 2 atmospheres, our initial volume. Our V1 is 2 liters. And we're changing V2 to 1 liter. and then we want to know what P2 is. And so if you notice, this is at constant temperature and without any loss of the gas sample. So we're at constant temperature, constant volume. And so that's why this relationship holds, is because N and T are constant. Okay, and so what we should be able to write is that P2 is equal to P1 V1 over V2. So 2 ATM times 2 liters, divide by our V2, 1.0 liters. And now the answer's right in front of us, but if you think of decreasing the volume, we increase the pressure. So this is like pressing downward on a piston to decrease the volume of the container. Of course, we increase the pressure now to 4 ATM. So our P2 is now double what it was because we cut its volume in half. Now, something I was going to point out and then forgot to on the temperature graph, and again, going backwards on my slides screws the videos up. But if you look back 2 slides, notice how the volume versus temperature slide, how the temperature went negative, but the sort of curve continues in the same direction. When we think of temperature with the ideal gas law, we're going to have to think of the absolute temperature. When we flip to a negative temperature in degrees C, we didn't flip to like a negative volume. We didn't change the sign on volume or anything crazy like that. So we have to think of temperature as never being negative, because we don't want to flip to negative pressures or negative volumes just because the sign of temperature went to negative on the degree C scale. So let's think of using temperature on an absolute scale, so something like Kelvin. So temperature in Kelvin is our temperature in degree C plus 273.15. And what this is this is absolute zero. So this sets the temperature that we can't go below. So we can never go negative in Kelvin because the lowest attainable temperature is 273.15 Kelvin. And so at 0 Kelvin, that's going to equal, so if we're at 0 Kelvin, what's the temperature in degrees C? So if I just use my conversion here, my temperature in degrees C at 0 Kelvin is negative 273.15 Kelvin. So that's the lowest attainable temperature in degrees C. So below that, not getting there physically. So 0 Kelvin starts our absolute temperature scale at 0, and then all temperatures are positive values upward from there. And so in chapter 10, like I can't think of any problem we can solve in degree C. There's almost going to be no problem that if we give you a degree C temperature that you can actually solve with that temperature in the unit of degree C. So we're going to have to think almost every time here that we're going to have to think we need to convert to Kelvin in order to make the relationship. Because if we think right off the bat, we have a 2-liter gas sample, such as one with a movable piston at 25 degrees C, and it's cooled to minus 25 degrees C. If I think of my relationship between volume and temperature, that we had this earlier, V1 over T1 equals V2 over T2, if I don't change my unit of temperature to Kelvin, I'm going to like flip to a negative volume. So if you get a negative volume, negative pressure, probably an issue with the unit of temperature. And so what we want to do here is convert 25 degrees C. So I want to convert my T1 of 25.0 degrees C to Kelvin. So that's 298 Kelvin. Then I want to convert minus 25.0 degrees C to Kelvin. And so that's minus 25 plus 273, so that's 248 Kelvin. So that's just minus 25 plus 273. And then V2 is what we're solving for. And our V1 is 2 liters. So 2 liters at 25 degrees C, that's my initial conditions. And then V2 is what we want to solve for, the volume when I cool the gas. So do you expect the volume to go up or down when we cool the gas? So we have 2 liters at 25 degrees C, we're going to cool it, so we should compress the gas. We should see that the volume drops. And so if I take V2 to be V1 over T1 times T2, you see how I just multiply both sides by T2. So V2 equal to V1 over T1 times T2 would be equal to 2 liters divide by 298 Kelvin, and then times T2, 248 Kelvin. So that goes to 1.66 liters. So now, a question like this. We're going to get answer B if we just plug in 25 degrees C and minus 25 degrees C and don't think about converting our units. Volumes don't flip to negative, so that's an impossible answer. And then the volume doesn't expand, and it doesn't contract as much as it does in A. So we're definitely losing volume here. The volume of the gas sample should decrease. Okay, Avogadro's law. Avogadro studied the amount of gas as a function of the quantity of the gas and found, as you would expect, that as you add more gas, as you put more air in the tire, the volume expands. So that makes a lot of sense. And this, again, is assuming that you have a pressure and temperature constant. And so another relationship found by Avogadro was that regardless of what the gas sample was, if you had a mole of helium, if you had a mole of nitrogen as mole of N2, if you had a mole of CH4 molecules, so each of these quantities, you have a mole. And so to have a mole would mean you'd have 1 mole of helium. The molar mass of helium is 4.00 grams per mole. So this is 1 mole. Nitrogen's molar mass is 14, so N2's molar mass is 28.0. This is 1 mole of N2. CH4's 12.0 for carbon, 1.0 for hydrogen, so that's 16.0. That's 1 mole of CH4. So if you have a mole of helium, a mole of nitrogen, a mole of CH4, that those samples have the exact same volume as each other. So the volume doesn't depend on the gas. The only thing that volume depends on is the number of moles. And so if you have an equal number of moles of those gas samples, so 1 mole of helium, 22.4 liters, 1 mole of nitrogen, 22.4 liters, 1 mole of CH4, 22.4 liters. So what matters is these number of particles, that you have an equal number of molecules inside the container. So you have 6.02 times 10 to the 23 helium atoms for the helium sample, but then you have a mole of particles. You have 6.022 times 10 to the 23 N2 molecules for the N2 sample. Then you have an Avogadro's number of CH4 molecules for the CH4 sample. So the thing that's in common isn't the number of atoms. So the CH4 sample ends up having in total more atoms, but it has the exact same quantity of molecules. So we have 6.02 times 10 to the 23 molecules of CH4. And that's what's important for determining the properties of that sample, is how many of these particles we have. If we have the exact same number of particles, we have the same volume. And these are the gases at the exact same pressure and at 0 degrees C. So any gas at the same temperature and pressure that you have an equal number of moles occupy an equal number of liters. So the volume of a gas sample at 1 atmosphere of pressure, 0 degrees C, is 22.4 liters. And so that's what Avogadro was able to find. Now, one interesting thing in this chapter, and sometimes this becomes a silly thing that we test that I dislike, is that this is STP. And the reason why I dislike testing this is that standard temperature and pressure of 1 atm, or like exactly 1 atm, and it's 0 degrees C, not 25 degrees C. And I hate that, because anytime we do tests on, like, using the phrase STP on a test, you would think it's 25 degrees C. Like, everybody in the world thinks standard temperature would be 25 degrees C, but for whatever reason, STP is defined as 0 degrees C, not 25 degrees C. So just know, if we use the phrase STP on a test, that we're meaning exactly or precisely 1 atm for the gas pressure. That's easy, everybody knows that part. But then it's the temperature. The temperature is 0 degrees C, 273.15 Kelvin, or not 25 degrees C, not 298 Kelvin. Okay, so with that, we'll look at a couple of questions, or like, let's relate all those properties together to the ideal gas law, and then look at a couple of the relationships that we can get with the ideal gas law. And so to summarize, so far we have the volumes inversely proportional to 1 over pressure. We have volume directly proportional to temperature, and volume directly proportional to quantity. And so if we start to put these all together, then you would have volume is directly proportional to N and T and an inverse to P. So you have volume is inversely proportional to pressure still, but directly to N and T. And then we could put all these onto the same side. Like we could put PV together, divide by NT, and that these would have to be equal to some sort of a constant. And that constant is what we call R. We call that the ideal gas constant. And so the pressure volume times the moles and the temperature of a gas sample are equal to the ideal gas constant R. And so then you can flip our N and T back over to the other side, and then just classically we write it PIV-NERT. So you just see it written this way a lot, where we write it as PV is equal to R times NT, or as nRT. And so this is just relating the relationships between pressure, volume, quantity, and temperature to the ideal gas constant R. And so pretty simple derivation once you kind of think about the relationships of pressure, volume, temperature, and pressure to each other. And then I was mentioning, on the relationship between P1, V1 equal to P2, V2, and the V1 over T1 equal to V2 over T2, how they might make more sense once you're looking at the ideal gas equation. If you can see that for the Boyle's law, if you remember, for the pressure-volume relationship, we said that PV is equal to a constant. Like if N and T, if you remember for when we were changing pressure and volume, you said N and T were constant, R is always constant, it is the ideal gas constant. You can see that if only pressure and volume can change, then those are equal to a set of constants of N times R times T. And so then if you change P2, if you change the pressure, you change the volume accordingly, then they're equal to the same constant. And so that's why they're equal to each other. And so you can use the ideal gas law to come up with any relationship between these quantities to each other. Like you can use it to do the V over T relationship. Like if you have V over T are the only quantities that can change, and then we flip the RT over P here, that these are constant and can't change, then you get the V1 over T1 equals V2 over T2, because V2 over T2 would be equal to the same set of constants. You can change three of these constants. Like let's say you have some initial pressure, volume, and the temperature can change. To me, like this is kind of like a tire in a way, because the volume of a tire does change as you fill it, the pressure can change, and then the temperature can change. So a lot of objects have the ability to change three of these variables, hopefully airtight, the quantity is constant, and so this would be equal to nR if the moles is constant and the ideal gas constant is still constant. And so let me rewrite that. It's terribly written. I'm just trying to write this as nR. And so then if you allow pressure, volume, and temperature to change, but not N and not R, then P2, V2 over T2 are also equal to nR. And then therefore, nR is equal to itself, so P1, V1 over T1 is equal to P2, V2 over T2. So you can come up with a lot of relationships just with the ideal gas law once you kind of see it and can use it. And so I think sometimes when we present the Boyle's law and that P1, V1 equals P2, V2, that's a little confusing. Once you put it all together, hopefully it's less confusing. Okay, now looking at the ideal gas law, the next thing you might want to know is, well, what is the ideal gas constant equal to? What is R equal to? And so one of the ways we can solve for R would be to consider the gas at STP we were talking about, that standard temperature and pressure. So we had that 1 mole of a gas, of an ideal gas, was occupying more precisely 22.414 liters at STP, and again, that's precisely 1 atm, 0 degrees C, that we can plug those numbers in to solve for our gas constant R, because R is equal to pressure times volume. If we just take PV is equal to nRT, solve for R is equal to PV divided by NT, and then you can plug in that pressure, so 1 atmosphere times the volume, 22.414 liters, and then 1 mole of our gas, and precisely 0 degrees C, but in Kelvin. And this gives us the units of R in units of liter atmosphere per mole Kelvin. And these are actually probably the most common units that we use for the ideal gas constant. So this is a number we're going to use a bunch. You may have seen it before, but 0.08206 liter atmospheres per mole Kelvin. So the liter ATM, volume times the pressure, divided by mole Kelvin. Some of the other units are shown. I don't think it makes a lot of sense at this point to go through a derivation. There's one other number that we tend to use a lot. It's the 8.314, but we'll actually come back and rederive it when we actually go to use that units of R. So in almost every problem, I never use a different unit of R than this one here until the end of the chapter. And we'll talk why I switch units. Why I end up switching units is usually if I need to use SI units, I go with the joules because joule's an SI unit. So if I'm thinking SI units, I look for a value of R that's in SI units. Otherwise, I'm probably just using the liter atmosphere per mole Kelvin value. And so there's other units. You could convert pressure here to different units and recalculate R, but again, not something that we tend to use a lot. So one of the things that we can do with the ideal gas law is try to relate to the molar mass of a gas. So you can relate densities to the ideal gas law because density is mass over volume. And then mass comes about from thinking of moles as a mass divided by molar mass. And so one of the things we can do with the ideal gas equation is we can think of taking PV is equal to M over molar mass times RT, because that's what moles are equal to. So instead of nRT, we have mass over molar mass. And then I can do things like let's multiply both sides by the molar mass, and then let's divide both sides by the volume. So notice I just switched sides with the molar mass and divided by the volume. And then this is density now. So that M over V is density. And so I can relate density to the pressure times the molar mass of a gas divided by RT. So we can relate density as a gas to the pressure of the gas and its temperature relative to what the gas is, its molar mass, and the ideal gas constant. And so we can come up with those relationships from the ideal gas law. So some of the things we can do, probably makes sense to look at these next time because I think we'll get too deep into taking a while to set these up. But we can rederive those expressions. I'll kind of start with the rederivation of those equations that I was just wrapping up that relate pressure and density and molar mass, and then work on these problems to start class on Friday. All right, guys, that'll do it for today. Have a great day.